In the previous lecture on electrical power supply systems, we considered a three-phase source. A three-phase source is actually obtained from a generation and transmission and distribution system before it is actually available to us at our homes or offices. And the transmission system in fact consists of transmission lines and transformers. Transformers in fact are an important component of any electrical power supply system, and we shall in this lecture have a discussion of single phase transformers and then move on to three phase transformers. We also discuss a few interesting features of transformers, but before we do that, let us just quickly look at what are the characteristics of a mutually coupled circuit. Transformers in fact a special case of a mutually coupled circuit. So today we will just in fact this is a continuation of a discussion we did quite some time ago of an inductor. An ideal inductor is a device in which is essentially a coil, and the magnetic fields are created by the current carrying coil. The rate of change of the magnetic flux seen by the coil causes a voltage to be induced. So this is essentially from Faraday's law. So if you recall what we did in the previous class, one of the previous classes in fact, was that we considered a coil. If we assume that the magnetic field is limited to this portion of the coil and practically zero elsewhere, we could define a voltage which is the potential of this point minus the potential of this point, I will call it V. And if a current is flowing through it, then we find that V is equal to L di by dt. And if we consider the voltage to be the potential difference of point A with respect to B, that is phi A minus phi B, that is the voltage between A and B, potential of A with respect to B, and the current is assumed to be in this direction. Of course, if it is in the opposite direction, we will have to take minus of whatever it is there. So if you have got this relationship in fact comes from Faraday's law, and if you actually check out actually working it out, you will find this L comes out to be a positive number. It is of course this L is a function of the geometry of the coil as well as the permeability of the material here. Okay. So this essentially is the relationship. Remember that if potential is measured, potential of point A with respect to B is V, and the current direction, reference direction is taken in this way, L will come out to be a positive number. So this is what we call self inductance. We also saw that you could have more than one coil, one turn, and this is like actually having two turns in fact. So the voltage which you get here now, if these turns are very close to each other, you will find that this constant here varies as n square, which is the number of turns. So this is what we did some time ago. This is an ideal inductor. In fact, it is not necessary that the flux seen by a coil should be produced by that coil. In fact, this is often called the self inductance, but in case you have got another coil which is independent but in the vicinity, then there could be a mutual inductance between them, in the sense that the current in one coil causes flux which gets linked with the other coil, and if this links with the other coil, you can have a voltage induced here. And in case the coils are wound in the same fashion, for example, if you have got a core and I wind a coil like this and another coil in a similar fashion, and if we assume that most of the flux is actually, or all practical flux is flowing through this core which is there of the coil, then in that case you will find that that a current in this coil will cause a flux which links with this coil and causes a voltage in this coil. So in fact, if all the flux linking the first coil links the second coil as well, then it is not difficult to see that the voltage induced here and induced here will actually depend on the number of turns of this and this. In fact, it will be proportional to the voltage V1 by V2 will be proportional to N1 by N2. This is of course true only if you have got flux, the same flux links both coils, and there is no flux which links this coil but does not link this coil. Okay. So, under these circumstances you have got what is known as a mutual inductance. In fact, you can a current in this coil also can cause a flux which links in with this coil. Okay. So, in fact, the relationship now becomes a vector kind of matrix relationship. V1 V2 is equal to L L11 I1 and L I2 2. If there is no mutual inductance between them, this would be 0, in the sense that if there are two coils which are very far apart and the flux caused due to this current, hardly there is any flux here due to this current because the distance is very large. In that case, this will be 0, there will be no mutual inductance. But in case these coils are in the vicinity of each other, the flux the flux linking one coil will also link the other. It could be all of it or it could be most of it. Okay. If it is all of it, we have some special properties, but in general your L, this I will call this the L matrix, can have this form. And this should be d by dt of this should be d by dt. So, you have to take the derivatives of the current. So, this is essentially what you this is the kind of relationship you get in case there is a mutual coupling between the coils. Remember that the current in one of the coils causes a magnetic field from Ampere's law, and this flux may link the other coil, and if it links the other coil, that is the other coil sees that flux going through it, then there could be voltage induced in case there is a change in the flux. Okay. So, of course, this is important, I missed it out in the first go. This, remember that d by dt is here. Okay. Now, as I mentioned some time back, if you are measuring voltage this way and current is going in for the first coil and V2 and you have got I2 going in like this, V2 is measured this way, potential of this with respect to this, current going in into the first point, that is this is A1 and this is A2. So, if you are measuring voltage of A2 with respect to B2 and the current is entering A2, then one of the things you can in fact show that this by using Faraday's law, L11 and L22 will in fact be positive numbers. Mutual flux need not be positive, in fact mutual inductance need not be positive, it depends on the sense of the coils. Okay. So, if you have got one coil wound in this fashion and another coil is wound in this fashion, okay, and if you are measuring V1, V2, I1 and I2, this voltage is measured this way. In that case, in this you will in fact find that the mutual inductance comes out to be negative. One point which I mentioned some time back was the mutual inductance M, this matrix here is in fact having the off diagonal terms are equal. So, this is an interesting property, it is not absolutely trivial to show that the mutual inductances will come out to be equal, that is the flux linked in the second coil due to the current in the first coil is also equal to the flux linked in the first coil due to the second coil. Okay. So, you will find that this it is an interesting property which you may try to prove, it is given in some books as well. Okay. So, this is where we this is in general a mutually coupled circuit. In fact, a transformer is a special case of a mutually coupled circuit in which the flux which is linked to the first coil also links the second coil completely. There is no flux which links the first coil, but does not link the second coil. So, the same flux kind of flows in a tube through both the coils. In such a case, we will call it a transformer. In fact, of course, this is an ideal transformer. This is never true that the flux linking one coil is exactly linking the other coil. Some of it leaks. So, in that case, of course, we are not having an ideal transformer, but an ideal transformer, in fact, the flux linking both the coils is actually the same. With this in mind, let us just quickly look at some of the properties of an ideal transformer. So, in a general mutually coupled circuit has this kind of structure of the equations. We call it a circuit model. We assume that all the flux is of course constrained in the region around the coils, and this voltage V1 and V2 is measured outside the coil at the terminals, and what we have here is L11 and L22 is in fact a positive number. If the dot convention is in this fashion, then it shows that the relationship is in this way. So, in fact, remember that if somebody gives you the L and M values and they give you this dot convention, that is the currents flowing in the dot, in that case this will hold true. So, remember that this relationship I am showing you holds for I1 entering the dots, okay, and V1 and V2 measured in this fashion. Okay. Now, this will become clear in the next slide where I reverse the dots. Suppose I have got a coil which is for which I have given the inductance matrix here, then what it means is of course that V1, V2 and I1, I2 are have the directions as shown, and the L matrix has to be written down in this fashion. If you choose the current direction to be going outward from this dot, in that case the second column of this matrix will have to be the signs will have to be reversed. Second column of this matrix, yeah, the second column of this matrix will have to be. So, if I1 and I2, if I2 is sign, if the direction of I2 in this figure is reversed, in that case when you are writing down the equation, you have to reverse the sign of M and L22. Okay. So, this kind of convention has to be kind of understood. In fact, what is its relationship to a physical device? A transformer which is of this kind or mutually coupled circuit. In fact, we have not yet mutually transformer is only a special kind of mutually coupled circuit, and if you have got coil number 1 and coil number 2 in this fashion, and we measure V1 and V2, I1 and I2 in this way, this will be represented in fact it could be represented, first we can represent it like this. This is coil number 1, this is V1, I1, this is the dot, V2. They are wound on the same sense, that is if you get them on the same limb, in that case they are wound in the same way. Okay. So, if you have got it in this fashion, you can rewrite, you can redraw it like this, and this is V2. So, this is in fact how you will describe this, and here you will have L, M, M and L. This will be the matrix, and you will have I1, I2 in this fashion and V1, V2 in this fashion. On the other hand, and if I draw the first coil here and the second coil here, this is the first figure. I am sorry, I will redraw this with a different sense of the windings. This is the first coil, and the second coil is actually wound with the other in the other way, So, this goes outside first, then goes in, then comes out again, and then it comes like this. If you look at this system, in fact, it can be represented as this one would have to be represented like this. I1, where V1 is measured like this and this would be V2 and this would be, I am sorry, V2 is measured like this and the current I2 would be going in like this. So, this is when you if you represent it in this fashion, you will again get your L matrix L22 and L, both the L's will in fact come out to be positive, okay. L's and M will come out to be positive. So, in fact, this is the so called dot convention, which actually tells you the sense of the coil. Sometimes of course, you may not be able to, if for example, if they are wound in this, so, and if you take this like this, okay, they are wound like this. So, the flux in fact goes in this fashion. Now, how do you decide on the dot convention in this case? Well, what you can do is of course, one of the ways to do it is actually slide this coil and bring it onto this, slide it, push it and bring it onto this limb. So, then it will look a bit like this, okay. So, that is why you know what is the, where you should place the dots, okay. So, if you push this coil and bring it to the same limb, you will find that in fact, it will look like this. In that case, this is the, so if this is A and this is B and this is A1, A2, this is sorry A1, B1 and this is A2 and B2. If you slide this like this will become B2, this will become A2 and this will become A1 and this will be B1 and this will be A1, this will be B1, this will be B2 and this will be A2. So, in fact, this is how your this is how you would actually assign the way the dot conventions, and when you use the equation V is equal to the V1 V2 is equal to the matrix, that L matrix d I1 I2 by dt, this is how you would write the equations. So, this is the meaning of the sign convention. If you have got coils of this kind, you slide it around here, it looks like this, then B2, this would be B2, this would be A2. So, in fact, if you redraw this, this will actually come out to be, in this case, this will come out to be A1, this will come out to B1 and this will come out to be A2, this is B2. I have just redrawn this. This is V1, this is this is V1, this is V2 and this is the current going in, okay. So, in fact, this is how you can actually decide on the dot convention. Remember that of course, in some cases you may find that it may be difficult if you have, for example, 3 limbs etc. to do this, but what you really need to see is really is the current, if the current increases in one of the coils here, in which is the flux in a certain direction increasing or not increasing, okay. So, of course, it is best to picturize it in case you bring the coils onto the same limb. So, you can try to do that and you will in fact get to the right answers as far as L and M are concerned. In this for this transformer, which is equivalent to this transformer, what you will this mutually coupled circuit, which is equivalent to this mutually coupled circuit, you will find in fact all these L's and M's are going to come out to be positive, okay. So, that is essentially what the dot convention means. It actually captures the sense of the coils. You can of course wind the coils in the opposite direction. In that case, you will have to reverse the signs. For example, if this was wound in the opposite way, that is instead of being wound like this, it was wound in this fashion, okay, the dots would reverse. So, this dot would not be here, but here. Okay. We now move on to an ideal transformer. If you try to write these equations for an ideal transformer, in fact, what we see is we will define two new quantities called flux linked. Flux is in fact B dot ds over the surface bounded by the curve on which the voltage is induced, or the electrical field is E dot dl is in fact induced. Okay. But if you got n turns, seeing the same flux, then we use a quantity called flux linked, because the fact is that the voltage is now seen across the terminals of n turns. So, you in fact have to take out n into the flux seen by each turn. Okay. So, when you are applying Faraday's law. So, you will find that psi 1 and psi 2 are in fact the n into the flux link is equal to n into phi. Okay. So, that is where phi is. So, if you have got two coils, you will have the flux linked, of course, is related to how much B dot ds, which is kind of flowing into this surface. So, this is actually B dot ds over a surface which is bounded by this closed curve. So, if you look at each coil as a closed curve, this surface you do B dot ds, that is flux. N into B dot ds captures the fact that voltage is induced in this as well as this, and possibly more turns if there are more turns. And so, the voltage induced at the terminal here of n turns is going to be n times d psi by dt, n times d phi by dt. So, that is why we use this psi to represent n phi, and the voltage which appears at the terminals of n turns is going to be n d phi by dt, which is nothing but d psi by dt. Okay. So, what we have here is in fact psi 1 by n 1, which is which is phi 1, which is the flux seen by the first coil, and psi 2 by n 2 is equal to the flux seen by the second coil. So, we are talking of two coils, each may have different turns. Okay. So, the number of turns of the first one is n 1, the number of turns of the second one is n 2, and if we apply the constraint that the flux which is flowing through one coil also flows through the other, it links the other one, and that is there is all the flux which is there links both coils, there is no leakage. In that case, phi 1 and phi 2 are equal. So, actually you will get V 1 by V 2 is equal to N 1 by N 2, which is a very fundamental equation of a transformer. Of course, it is an ideal transformer, as I mentioned, that no flux leaks. We will in fact see what is leakage in a few slides from now. If all the flux linking the first transformer, first winding links the other winding, and none of it leaks anywhere else, in that case you have got V 1 by V 2 is equal to N 1 by N 2. So, V 1 by V 2 is constrained to be N 1 by N 2, N 1 by N 2 in an ideal transformer. In fact, we can easily see from the because phi 1 is equal to phi 2, the equation which is shown at the end holds, and if you go to the next page, it is easy to see that if this equation holds for all values of I 1 and I 2, then another interesting relationship which comes out for an ideal transformer is L 11 L 22 will come out to be m square, and so also L 11, which is the self inductance of the first winding, is equal to N 1 by N 2 into the mutual inductance, and L 22 is equal to N 2 by N 1 into the mutual inductance. But this is of course holds for an ideal transformer, not in general for mutually coupled circuits. So, there could be mutually coupled circuits where the flux linking the first coil, all of it does not link with the second coil. Okay. So, just to give you a visual indication, so if you got one coil on one core and another coil on the same core, I have assumed for an ideal transformer that the same flux links both the coils, but actually there could be some flux which does not link both the coils. Some of it in fact goes these flux lines do not link this coil. Okay. So, this is called a leakage. If this is true, of course, these relationships do not hold. Okay. In general, mutually coupled circuits, you need not have L11 is equal to N1 by N2 into M. Okay. So, this is one important point which you should remember. In fact, this is something which we should remember, of course, that V1 by V2 is equal to N1 by N2 in an ideal transformer. If you give arbitrary values of V1 and V2, this equation will of course not be satisfied. If you notice that the matrix here which is shown, the matrix here is in fact singular for an ideal transformer. In fact, if you look at the rows, and the first row is related to the second row, so you really can't invert this. Okay. So, V1 and V2 have to have a certain constraint, and that is N1 by N2. This is of course for an ideal transformer. Yeah. Now, since the equations which I showed you in the previous slide were actually for in general, there was nothing related to sinusoidal inputs or sinusoidal steady state, but if this equation holds in general, it will also hold for sinusoidal steady state situations, and therefore, you can represent a transformer in the phasor domain by the next by this in this fashion. If you have got a sinusoidal input, then the phasor representation is this, and if you in fact keep the transformer open circuited on the secondary, that is if I2 is equal to 0, the current flowing is given by V1 bar, which is the phasor corresponding to the voltage across the first coil divided by j omega L11. So, in fact, a transformer which is kept open circuited on one coil open circuited, or rather only one coil is excited, all the other coil is kept open circuited, it is simply a self inductance or an inductor, a plain inductor, not a mutually coupled inductor, in case the secondary coil is kept open. Okay. So, a transformer with an open circuited secondary is like just like an inductor. But one another important point which you should remember is that you can have more than 2 coils, you can have 3 coils, and they could all be mutually coupled. In case in that case, of course, you would have a 3 by 3 matrix for the three coils, and in fact that would be also symmetric matrix. So, mutual inductances between the coils taking 2 at a time in fact would come out to be equal. So, the mutual coupling between 2 coils is always equal. Okay. So, you always have a symmetric matrix. For an ideal transformer, we also have L11 generally very large, but we will come to this a bit later. So, if you keep the secondary open circuited, the current flowing in the secondary is in fact in the primary winding is IOC, it is called I open circuited. Okay. Yeah. If you of course load the transformer, then I have just expanded this equation here, and I have added a additional subscript load to show that it is loaded. In that case, the relationship between V1 and I1 will actually be slightly different. In fact, V1 will be not only a function of I1, but also a function of I2. So, this is given by the last statement here. Yes. So, if you have got a loaded transformer, in that case the first equation we rewrite, that is j omega L11 into I1 load, that is the current in the primary winding, plus it comes out to be N2 by N1 into I2 load. This actually comes from the previous equation. Yeah, this is how we get it. That is because of course that M which you have here is for an ideal transformer N2 by N1 into L11. Yeah. Now, since j omega L11 is nothing but V1 by IOC, okay, V1 by IOC, we can substitute that in fact in this equation here, and when you cancel V1 and V1 on both sides of the equation, what you eventually get is IOC minus N2 by N1 I2 load is equal to I1 load. Okay. I1 load is the loaded the current under loading conditions in the primary, and I2 load is the current in the under loaded conditions in the secondary. So, what I did was I substituted for j omega L1 from this equation which you see here. So, I substituted V1, and then you cancel V1 on both sides, and then you get a simple relationship like this. In fact, if IOC is negligible, in that case the currents IOC is negligible compared to the loaded current in the loaded condition. In such a situation, we have I1 load comes out to be minus N2 by N1 into I2 load. Of course, if IOC is finite or comparable to the the current under loaded conditions, in that case of course this is not true. So, this is an important aspect which you should remember, that the currents in fact under loaded conditions are related by a very simple relationship if the current under the current under loading conditions is much larger than IOC. Okay. So, this is an interesting fact. Yeah. So, this is the equations of an ideal transformer, but with IOC finite. In fact, probably the correct word is not IOC is finite. If IOC is not negligible compared to the load current, then this equation would hold. Okay. If you have got in fact a resistive load at the secondary, then it is also true that V2 minus V2 bar by R load is equal to the secondary side current. And if you actually substitute this in the basic transformer equations, if you just follow these equations, what you get in the end is that I1 load can be written completely in terms of V1. Okay. So, you can write the load. So, if you connect a resistance on the secondary, the primary side current can in fact be written completely in terms of V1. So, what it really means is, and if you look at how it is related, you will find that I1 load is nothing but the open circuit current, what would have been the current under open circuit conditions on the secondary, plus current component which is N2 by N1 square, the turns ratio square, into V1 by R load. Okay. So, this can be again rewritten. In fact, it is as if in addition to L11, we have a parallel connected R load multiplied by the turns ratio square connected on the secondary. So, just to show it pictorially, which I think you will understand it better, if you have a resistance connected to the secondary of this transformer, then it appears, this transformer appears to the primary winding as if that R load has been multiplied by N1 by N2 square. Okay. If R load is infinity, we are back to open circuit conditions, and the current in fact flows to this L11, that would be simply IOC. Okay. So, under loaded conditions things would look like this. In fact, you can prove this for any kind of load, it need not be just a resistive load, it could be a RC load or a RL load, and what you see is that in fact your the resistance impedance or resistance of the impedance gets seen on the primary side as if it is multiplied by this turns ratio square. This is called, a process is called referring a load to the primary. Okay. So, this is like referred load. So, this is a kind of equivalent circuit as seen from the primary. Okay. Of course, this is equivalent works for an ideal transformer. In fact, one more interesting thing which you will notice is that in case you have got a transformer as shown there, if you multiply V1 by I1 star, we get what is known as apparent power. So, apparent power on the primary side, and then if you evaluate this apparent power, you will in fact find that the apparent power on the primary side is equal to in fact the V1 IOC star. IOC is the current which would really flow in case you kept the transformer under open circuit conditions, minus V2 into I2 load star. If you look at the direction of the current, of course, remember we have been taking the current into the dot as positive in our equation so far. So, in fact, if you reverse the direction of the current, and if you assume IOC is small or negligible compared to the load currents, in that case primary side load current, in that case what you will see is that V1 I1 star is equal to minus V2 I2 star with the current going into the dot, or plus V2 I2 star if the current is going away from the dot. Okay. So, what it really shows is that the apparent power, if you assume in fact if the open circuited current is almost 0, it is approximated to be 0, if it is very small, in that case we will see that the real power which is demanded by the secondary is equal to the power which is drawn. So, the transformer by itself is a kind of a passive device, it does not supply any energy. So, whatever real power is demanded by the secondary is actually coming from the primary. Okay. This minus sign of course is because of the fact that we have taken the current flowing into the dot even on the secondary. Okay. For a purely resistive load, of course, if you assume IOC is again approximately 0, then real of V I star is equal to in fact the power loss in the power dissipated in the resistive load. So, this is really just showing something which is intuitively very makes sense, that a transformer by itself does not of course supply any real power. Whatever is being supplied on the secondary is in fact got from the primary. Yeah. A practical transformer, if you look at, is in fact there are several important points. We would like IOC to be 0, although it is not exactly 0, because if you have got IOC is equal to 0, then in sinusoidal steady state we have a nice relationship between I1 and I2, a very elegant relationship, that is I1 by I2 is equal to minus N2 by N1. So, that is a very nice relationship, but that holds only for current under open circuit conditions is very small. Okay. So, that is not actually strictly speaking the case. What you have in a practical transformer is that there is a kind of a open circuited current, current under open circuited conditions also, and that is given by M into N1 by N2. Now, what we will do is we will treat this as an ideal transformer. An ideal transformer has V1 by V2 is equal to N1 by N2, and I1 by I2 is equal to minus N2 by N1 if the current direction is of course into the dot. Okay. So, this equivalent circuit of a transformer, this portion is in fact we call it an ideal transformer, where V1 by V2 is equal to N1 by N2, and in sinusoidal steady state conditions I1 by I2 is equal to minus N2 by N1 with the currents going into the dot. Okay. So, we even extract, this in fact extra inductor which we take out or represent separately is in fact L11, because M into N1 by N2 is L11. So, what we will this portion is called the self inductance. Okay. This, and even if I keep now, even if I2 is equal to 0, it just indicates that there is some current still drawn from the primary winding, and that is the magnetizing current. So, in a practical transformer, of course, the open circuited current compared to the full load current, full load is what is known as the rating of the transformer. Remember that every transformer is rated for some current, in fact, its winding, the thickness of the windings, etc., have been decided based on the rating, okay, what you can, what is the maximum kind of current which can flow. So, usually in a practical transformer, the open circuit current is in fact quite small compared to the rated current. Okay. Of course, we have got this point of rated current because in a practical transformer, remember, you have to is made out of conductor which has got a finite, it has got a finite conductivity. So, in fact, it has some resistance and some heat is lost because of I square heating in these coils, and so you need to design. So, when you have got a coil of wire, it cannot carry more than a certain amount of current. If you in fact allow it to carry more than a certain amount of current, it will become too hot. So, the thing is, when I say rated current, what it means is that transformer is designed to carry a maximum amount of current. Compared to that, the open circuit current is usually very small in a especially in larger transformers. Okay. So, larger the transformer gets, means for power, typical what is used in high voltage power systems, etc., the open circuit current is very low. So, in fact, this M into N1 by, in fact, I should call this L11 because we shall see that M into N1 by N2 is not equal to L11 in case all flux does not link both coils. Okay. So, this also is a thing which we will have to slightly modify. It is better to call this actually L11, because later on we shall see that M into N1 by N2 is also not equal to L11 because of a non-ideality called leakage. Another aspect of a practical transformer which I had mentioned in one of the earlier lectures on self inductors, and we were discussing self inductance, was that usually this coils are wound on a ferromagnetic core. Okay. Why do you wind it on a ferromagnetic core? The reason is of course that the ferromagnetic core has a relative permeability which is quite large compared to free space or air, and as a result of which what happens is for a smaller current you can have larger fluxes. Okay. That also in fact indicates that because for smaller current you can have a larger flux with a ferromagnetic core, which also means that the inductance of a ferromagnetic core of a inductor wound on a ferromagnetic core is usually for the same number of turns much higher than that of a air core inductor. Okay. Which also means that the inductance value L, the self inductance value L11 for a 2 is can be quite high if you got a kind of ferromagnetic core. And in fact, the ferromagnetic core also since most of the flux, because mu is much larger, most of the B which is there in the core which flows through the coil will flow through the ferromagnetic path and not through air. So, in fact, one of the ways of looking at it is if you use Biot-Savart's law, the amount of flux at a particular place is actually depends on the mu which is there. So, in air in fact the magnetic flux density is low compared to that of in a ferromagnetic material. So, in fact, you have got much more flux, so you use a ferromagnetic core. So, in fact, what I showed was a limb of a core was actually typically made out of some ferromagnetic material. But one interesting thing about the ferromagnetic material is that it has two or three important issues related to it. Is the ferromagnetic core itself may be a conductor. So, because so what happens is that if there is a changing flux in the ferromagnetic core, there is a changing flux in the ferromagnetic core, there are eddy currents induced even in this in the cross section of the core. In fact, because by Faraday's law EMF is induced in closed loops, and if you place if this closed loop is in a conductor, immediately the electrons in that conductor get a force and they start moving, and these are called eddy currents. So, in fact, you can look at this as if as another short circuited coil. Okay. So, in fact, because of this you have to you can treat that also as a kind of a transformer action. In fact, the current in the coil of the transformer winding causes a flux, and that flux is changing. So, there is a eddy currents in the core. So, these are in fact like secondary some other coils. Okay. These are like a tertiary coil, So, what you can do is in fact this resistive loss which is there because of the current flowing in the ferromagnetic core itself can be abstracted out and represented in this form. This is only a rough model of this of the ferromagnetic core. You can look at it as, see, even if you assume that this second coil is not there at all. Okay. If you assume that this second transformer coil is not there at all, the eddy currents are like coils of current within the ferromagnetic core. Okay. So, the referred loading resistance can be represented here in this fashion. Okay. Of course, the amount of this resistance value is actually dependent on parameters of the core itself and the frequency. Okay. Now, of course, this represents a loss in the transformer. In fact, it is not you may have in fact seen some adapters etc. Even if you do not load or keep the secondary of such a transformer open circuited, then in that case you still find that if you excite the primary side, you will find that the transformer is becoming warm because of this core loss or core losses, eddy current losses in the core. Okay. So, this is an important aspect of any practical ferromagnetic transformer. Of course, there are transformers which are made out of core materials which have got high permeability, but they have very low conductivity. Okay. So, if you look at various practical transformers, just to give you an idea, this is a transformer, and when you look at it, of course, you will not be able to make out what how it is wound, but usually what you have is a kind of a shell kind of structure. So, what you have is a one of the ways which you can wind it is like this. This is the primary, and you have got the secondary also, which is wound in close proximity. Of course, all these coils are insulated from one another. Okay. So, this is something which of course you should remember. So, this both the coils may be wound on the central limb, and the flux can in fact flow in this fashion. Some time ago I had shown you a transformer with a single window, that is also feasible, and this kind of transformer also you can have transformer action here also. So, the ferromagnetic core ensures that most of the flux is here, much less flux is seen in the air. Okay. So, most of the flux flows in a tube which is defined by the ferromagnetic core shape. So, if you in fact look at this transformer, it also has got a nameplate, and the nameplate in fact tells you how much voltage you can apply and what frequency it is rated, and what is the capacity of the transformer. It is 2000 volt ampere, that is if the voltage, that is the apparent power it can handle. So, of course, it is given only for one, there is no, you do not have to specify it for both sides of the transformer for a 2-winding transformer, because in a 2-winding transformer under sinusoidal steady state, you know that V1 I1 star is approximately equal to minus V2 I2 star if the current directions are into the dot. So, the apparent power magnitude on both the primary and secondary coils is the same, assuming that the open circuited current or the current under open circuit conditions, or which is also called in fact the magnetizing current, is low. Okay. So, if you assume that the open circuited current or the magnetizing current and eddy current effects, that is the current drawn by these shunt branches here is very low, then the apparent power on the primary and the secondary side is equal. Okay. Now, one more interesting point you would notice is that it has also got a voltage rating. So, voltage rating has got two reasons. One is of course, if you apply very high voltages, remember that these coils of wires are insulated from one another, and if the voltage is very high, the insulation may fail. I mean, there is the electrical field is caused because of the high voltage. Remember that I had mentioned this earlier, that the coils of the wire, in between them there is this insulation material and there is an electrical field. In fact, it is like a inter-turn capacitance is there. If the field is too high, many insulators may fail if the electrical field stress is very high. That is one reason, but for low voltage transformers, that is not the primary reason why voltage rating is given. The voltage rating is given because you can't apply an arbitrary voltage to this transformer because of the fact that it can get saturated. For example, if your voltage is 230 volts as is given here, the primary input primary side is 230 volts and the frequency is 50 hertz, then it is not very difficult to see that the flux linked psi d psi by dt is equal to V1. Suppose we assume of course that d psi 1 by dt is equal to V1. Okay. Now, d psi 1 by dt is equal to V1 under sinusoidal steady state conditions. It means that omega into psi 1, j omega psi 1 is equal to V1. Now, j omega psi 1 is equal to V1 means that psi 1, which is n into phi 1, in fact the flux in the core is going to be determined by V by omega divided by N1. Okay. So, if you apply 230 volts divided by the number of turns of the primary divided by omega is amount of flux in the core. So, the point is that you can't have arbitrary levels of flux in the core, therefore, this input voltage is in fact specified. If a frequency is higher, the flux level will be lower for a given input voltage. Okay. So, the flux level, now what is the problem in having a high flux level? Well, in free space it does not matter, but in a ferromagnetic material, one thing we notice is that in case your flux level is higher, the flux and current relationship is no longer linear. Now, if you recall this V is equal to L di by dt, where I said this L is a positive constant. Now, this L is a constant only under certain circumstances. If it is free space or air, this L is indeed a constant if you are given a coil. But in a ferromagnetic material, unfortunately, if you in fact, how does this equation in fact come about? V is equal to N d phi by dt, and phi is in fact obtained by integrating the flux over the area bounded by this coil. So, if you have got flux is related to the flux density. Okay. The flux density is in fact there because of the currents. The interesting point here is that for a single coil, if we have got for a given the flux linked which is equal to N into phi versus current is not a linear relationship. I causes B, B dot ds integrated gives phi, phi into N, N is a constant will give you psi. Okay. Now, this and d psi by dt is equal to V. So, in fact, this is psi is equal to L into I. Okay. So, now, the thing is that this L is a constant for free space and air, it depends only on the geometry and mu naught, but for a ferromagnetic material, it turns out that as you increase the current and the flux level of the core increases, this is no longer a constant. In fact, you should write psi is equal to a function of I. Okay. This is called saturation. In fact, after a certain point you will find that the flux density in the core does not increase. In fact, for a ferromagnetic material, for a small current you can get a higher flux density because of the fact that mu relative permeability is high. Okay. But this relative permeability kind of saturates. In fact, after a point you will find that the change in I is not creating the same amount of change in flux as you would have expected. So, this is a something called saturation. In fact, there is another interesting phenomenon is that if you excite a core and then you de-excite it, it need not follow the same path, and that is called hysteresis. So, if you got especially sinusoidal excitation where the currents is sinusoidally varying, you will find that it is not following the same path for the increase in current as it is for the decrease in current, and this is called hysteresis. So, in fact, the core material is not ideal, but the fact is that in case you get saturated, you lose all the benefits of having a ferromagnetic core, because now the flux increase is not proportional to the current increase. Okay. So, that means that after a point you will start requiring much larger amounts of current to create a certain amount of flux. So, if your voltage is larger, you will in fact implies that in sinusoidal steady state it would mean that flux link would be higher. If flux link would be higher, it would mean current would be higher, but since because of saturation it will not be proportionately higher, but much larger than you would expect. Okay. So, you in fact lose the benefits of having a high permeability in case you are operating at flux levels which are very high. So, because of that what is done is in fact you use a ferromagnetic core, but you ensure that you do not apply high voltages or so that you do not operate at high flux levels. If you operate at high flux levels, you are effectively in the saturation region, and then you require much larger current to have that level of flux. If you got much larger levels of flux currents to have a certain flux, then the benefits of having a ferromagnetic core go away, and in fact you get in effect your inductance value goes down, but that is not a very good way of putting it. What we are effectively saying is that the amount of current the the inductor draws to set up the amount of flux is going to be much larger. So, in fact, this L11 or the inductance of the coil is not, it cannot be considered large and a constant value. Okay. So, that is why we have to limit the amount of voltage we can have. So, when you are designing the transformer, you design it so that if you apply that voltage and the number of turns which you have taken and the frequency which you have, the flux levels are below the saturation values. For the transformer steel, it could be above 1.5 Tesla, around 1.5 Tesla or slightly more than that, depending on the nature of the steel itself. That is the amount of saturation flux density B which can exist before in effect you get saturated. Okay. Yeah. So, in fact, if you look at another kind of, from a construction perspective, you of course, you have this what is known as a, for 50 hertz transformers, we have what are known as EI kind of laminations. These laminations are another kind of engineering, ingenious way to reduce eddy currents. I mentioned some time back that because of the fact that flux changes in the core, there are eddy currents in the core because voltage is induced even within the core material. Okay. So, to reduce the amount of currents, what we do in fact is kind of squeeze the currents to a very narrow region. Okay. So, what we can do is instead of making a continuous solid core of ferromagnetic material, we in fact stack up laminations and insulate each lamination from each other. So, what happens is now that the current now is squeezed here, or rather what it means is of course it sees a much larger resistive path, and because of which effective eddy currents reduces. So, in fact, you stack up these insulated laminations together instead of having one solid core. From a construction perspective, you can make an what is known as an EI curve. Okay. Yeah. So, this is a typical 50 hertz transformer. Okay. So, what we do is in fact, I mentioned the two window kind of what you have essentially is this this EI core, this I lamination is actually kind of we try to bring it as close to each other, in fact touch this and make a kind of two windows, and this the windings are wound on this a bobbin. This is a bobbin, this plastic thing is a bobbin which holds the winding. Okay. So, this is just illustrating how in fact this transformer is made. So, you have got a bobbin, bobbin is like a cylinder on which the windings are wound. So, what you have here is in fact a stack of this EI cores are kind of stacked, and we try to press this I lamination against this to try to avoid any air core. Other, if there is an air gap here, what we find is that to create a flux in the air gap will require much more current, something I mentioned some time ago, because the permeability of the ferromagnetic material is much higher, of air is in fact much lower. Okay. So, and this bobbin is kept here and the winding is wound on that bobbin. Okay. So, this is how we make a typical 50 hertz transformer. Yeah. For a high frequency transformer, we use ferrite cores because the eddy current in fact becomes very high. So, it is best to use a core material which is non-conducting. So, the earlier material was steel, but here we in fact have a ferrite core which has got very low conductivity. So, in fact, eddy currents are negligible, and this is required for high frequency transformers where the rates of change of flux are high. So, the chances of having more eddy current losses in the core is much higher. So, what we do is in fact use this kind of materials. The B saturation for many ferrites is in fact much lower than that of the steel which is used for 50 hertz. But because of this eddy current problem, we usually use ferrite cores. Yeah. The ferrite cores have low conductivity. Yeah. And of course, one more thing which we will try to, which you can actually do some further reading on, is that for high frequency we also use Litz wire, which is in fact kind of standard wire, which the cross section is made in such a way, the stranding is done in such a way so that you can avoid skin effects, something which we shall learn a bit later, but it is good to remember this, we will come to it a bit later. And in this case the ferrite core you use 2 E cores and kind of make the entire structure instead of EI. Yeah. Now, so one of the things I mentioned about the core is of course that you can have saturation, and because of the fact that when you increase the flux and you decrease the flux in fact does not follow the same path, and this is called hysteresis. So, and also eddy currents flow in a ferromagnetic core. So, in fact you will find that the core is not a linear material. In fact, if I apply a voltage and if I look at the current flowing through it, you will find that the current is lagging the voltage which is under open circuit conditions. So, if I in fact keep a transformer with secondary open circuited and I apply sinusoidal voltage to it, in fact this is not a nice sinusoid, but it is almost a sinusoid. If you apply sinusoid to it, the current lags the voltage, but you will notice that it is not lagging by 90 degrees, which means that it is not a pure inductor because of eddy current effects and hysteresis effects. You do not have this as an ideal linear inductor. In an ideal linear inductor, you would find in fact that there would be a 90-degree phase shift. Remember, there is a transformer with its secondary open circuited is simply like a normal inductor, okay. But because of the ferromagnetic core, we have got eddy current losses, saturation, hysteresis, and therefore, you will find that this, you will in fact find that the current is not exactly 90 degrees to the voltage. In fact, it is slightly less than 90 degrees, which indicates that there is a loss because it is behaving a bit as if it is having some resistive component. Yeah. If we in fact increase this voltage slightly more, you will find that the current starts looking a bit different, and we go on increasing it, and now you find that the current looks completely non-sinusoidal. This is not surprising because of the fact that the ferromagnetic material is now saturated. Because it is saturated, if you have applied a certain voltage, sinusoidal voltage, the flux in the core is also sinusoidal because V is equal to N d phi by dt. So, the flux is sinusoidal, but to create a sinusoidal flux near its, when the sinusoidal flux is reaching its peak value, the core is getting saturated. So, you find that you require much more current to create that flux. So, this in fact you see this non-linearity, and because of this non-linearity the current response is not sinusoidal, it has got harmonics. In fact, it is not even having quarter wave symmetry, you will find it is not, because of the fact that it is also having hysteresis. So, there is hysteresis, eddy current and saturation occurring, and now your waveform looks quite distorted. Yeah. Just to show you that the ferromagnetic core, the ferromagnetic path in fact increases the inductance. So, what we will do is take a transformer. In the transformer you have got two sets of coils, the primary and the secondary. This is the core, and what we will do here is we loosen out this this core is made out of EI lamination. So, the I laminations have kind of been loosened out, and what we will do is excite the primary side and keep the secondary side open, and in case you excite the primary side and keep the secondary side open, this is a transformer is as good as an inductor because you do not have any current on the secondary. Okay. Now, the inductance of this inductor, which is in fact the self inductance of the primary winding of this transformer is high because of the fact that you have got a ferromagnetic core. I mentioned to you, because you have got more flux for the same amount of current, because of the high permeability, your L, the constant L is quite high. Okay. So, this happens because you have got a ferromagnetic path, but in case you move, I mean if you actually make it an air path, okay. So, partly you remove the I core, so now the flux in fact will flow through the air. In that case, the inductance, self inductance of the primary winding in fact reduces, that L11 reduces. So, IOC will increase in case you have a air path instead of a ferromagnetic, if you close this path through air instead of the ferromagnetic path. So, this is what is shown, demonstrated in these figures here. I have got a movable core, I remove the core, if this core is in place, what you find is this is the current and this is the voltage, okay, and what you have in fact is this is IOC, okay, not I excite. I excite in fact means IOC. So, in fact this, but if I remove this core, the excitation current in fact becomes, or the IOC becomes very large. Why is that so? Because L11 has suddenly reduced. So, it is a very simple experiment which you could try out of. So, now what happens is that some part of the flux goes through the ferromagnetic core and some of it is actually going through the air. In fact, the flux path is completed through air. That would be a more appropriate way of saying it. So, the flux partly goes in the ferromagnetic core and completes its path through air. But because the air path, because to create a flux in the air path requires much more current, what you see is that IOC suddenly increases. So, we go back one slide and you see the next slide. Okay. So, you really see that the current has, we have not changed the scale. So, what you really see is actually an increase in the IOC. I excite is nothing but IOC. Yeah. This is another concept which we should be aware of, that is leakage in a transformer. I have already mentioned this aspect some time ago, where you in fact the ideal transformer equations were in fact with the assumption that your flux, which is, let us say you have got two coils like the ones I had drawn some time ago. Suppose you have got these two coils, and what you find is that if your flux linking one coil is equal to the flux linking the other. So, if I compute the flux B dot ds here as well as here is exactly the same, then we have the ideal transformer equation V1 by V2 is equal to N1 by N2, which is true during transient conditions as well as in sinusoidal steady state conditions. Okay. Now, the thing is that what we actually find is that the flux, all the flux does not necessarily link both windings. Okay. So, there could be some flux which is flowing partly in the ferromagnetic core and then going into the air, some of the flux going in this fashion. So, this flux which you see here is in fact not linking both windings. So, what it means is that this V1 by V2 is equal to N1 by N2 is not really going to be true. In fact, a part of this flux is common and there is some part which is leaking from the first coil, and in case there is a current in the second coil, there could be a flux here which is linking the second coil, but not linking the first coil. So, if there is some current flow in this as well as this, there could be leakage fluxes both in the primary and the secondary. Of course, this leakage fluxes phi L2 will be there in case you load if there is some current flowing in the secondary winding. Okay. So, of course, these leakage fluxes are there provided there is current flow in the windings. So, that is an important thing, and that leakage fluxes phi L1 and L2 are in fact not linking both windings. Okay. So, in fact, phi M1, so the flux linking the first is equal to phi M plus phi leakage 1, and the flux linking the second is phi mutual. What is linking both and what is not linking? These are of course going to be related to the current flowing in these windings. Okay. So, this, in case there is no current flow here, then this term will of course not be there. So, there will be no leakage flux of the second winding. If there is no current flow in the primary winding, this will in fact not be there. Okay. You could have some flux which is linking both the windings, that is the flux due to the other winding. Okay. So, this kind of relationship is existing, and because of that you no longer have V1 by V2 is equal to N1 by N2. In case these two things were absent, this would be true. Okay. But this is no longer true, and this, because of this, you can have voltage induced in one winding due to the flux not linked with the second winding. So, you will find that this V1 V2 kind of deviates from N1 by N2. So, this kind of leakage effects can be represented quite well by a series inductance which is in fact given in the next slide. Okay. So, let us consider a simple setup which demonstrates this leakage aspect. This is a transformer, you see a ferromagnetic path there and you have got two coils. Okay. So, this is just a kind of transformer we constructed specifically for these experiments. Now, this primary side we call it the input side. The word primary or secondary is only a matter of convention. So, I will call this the input side or the primary side and I excite this primary winding, and what we will do is try to see the kind of effects of having high and low leakage. As I mentioned to you in the previous figure which I drew, this is in fact the leakage flux. Okay, it flows partly, some of it may flow through the ferromagnetic material, but most of it then has a return path through air, but not through the complete the ferromagnetic path. So, this is called a leakage flux. Now, this is a transformer, in fact leakages are low in a transformer, we expect them to be low, but I can make a transformer with, this is a mutually coupled circuit. So, this is our the special transformer which we have here. Now, this is a mutually coupled circuit because the ferromagnetic core has low reluctance. You will find the leakage is there, but not much. There is leakage of course. Now, what if I actually have a transformer in which I in fact wind the coils in this fashion? Now, you can have flux paths which are like this through ferromagnetic, the path is ferromagnetic and this flux here will not link with the flux here. So, a significant component of flux will flow through these paths. Of course, there will be flux in this path also. So, this kind of arrangement where you got two windings on two limbs and this third limb is also created, this is not a good transformer because most of the flux is now, some of the flux or a significant portion of the flux is leakage flux because it does not link both the coils. Okay. So, if this coil is excited, you can have some flux flowing like this and some of the flux is flowing like this and does not link this coil. So, this is a bad transformer, and in case you actually put this element in the middle, let us see what happens. So, what you will see in this experiment which you can also perform, if you got a middle limb which you place you just push it into this this place, so that there is a path for the flux to flow here. In that case, what you see is that if you have an input voltage of V, which is in fact the input voltage is 230 volts, the output voltage, the turns ratio is in fact 230 by 35. Okay. But if you in fact excite it by 230 volts, what you get here, or less than 230 volts, I am getting 4.85 volts in the secondary. Now, the middle limb is not placed. Okay. I have in fact given lesser than 230 volts at the input and I am getting 4.8 volts at the output. Okay. The input voltage is not 230 volts, otherwise of course I would have got 35 volts here. Okay. So, it is slightly less. So, I have applied slightly less voltage. The same voltage I apply as before, but now I place this middle, I put a middle limb here and you see a perceptible reduction in the output voltage. Okay. So, by putting a middle ferromagnetic limb, your voltage drops perceptibly at the output. Why does that happen? Because some of the flux which is earlier linking this is now flowing through this. Of course, this is not perfectly fitting in here, there is a small air gap here. So, the flux still preferentially flows through this path and not much flows through this, but still it is significant enough to see a perceptible difference in the voltage which is induced in the secondary coil. So, this is a very this illustrates that if you actually give a leakage path where the permeability, effective permeability is much higher, you may actually have more leakage flux and therefore, your voltage induced on the secondary will reduce. Okay. So, for the same input voltage now you are getting, instead of 4.8 you get 4.2. We could have got even lesser if there was no air gap here, but of course some air gap has to be there because we inserted this limb in an extraneous way, it is not a part of the original transformer. Yeah. So, in fact, another interesting experiment we can consider is when we have two specially constructed transformers to illustrate again the effect of leakage. If you in fact have a transformer of a certain of a certain rating, this is specially constructed. I call this a short transformer or a fat transformer. It is not fat really, but it is kind of having lower height, shorter, and I wind the coils on these two limbs. Now, if you have a short transformer, this height is less, what happens is that the flux of course flows through this path, but since this distance is lower and most of the coil can actually flow through the ferromagnetic path, and it may flow through the air path as well. Okay. And this height being less, the path which the leakage flux has to traverse through the air is actually quite less. What do I mean by less? When you compare it to a transformer of the same rating, but what I have done is now I have wound it on this limb here. What I have done is in fact the same transformer, I have in fact wound windings on these limbs. Okay. So, you can say this is a taller transformer or a thinner transformer. So, I will call it fat, although I really mean it short, and this is a tall, that means the winding is wound on the tall limb. Now, what happens is that the leakage flux, if it has to flow, it has to actually go through a much longer path. Okay. So, we can expect that the leakage, in fact, in this case the leakage flux is going to be less than this, because here most of the leakage flux can in fact take the ferromagnetic path, then have a short air path and get back. Okay. So, you can in fact have more leakage here than here, we expect that to happen. In fact, of course, this is more intuitive, I have tried to tell you these aspects intuitively. One aspect which my student has just brought to my also to my notice is that here here the coils are packed closely here, whereas here they are spread out a bit more. So, you will find that in fact they are spread out over this whole length, and if we actually do a more rigorous analysis, not just the intuitive kind of thing I have shown here. In this, here I have tried to appeal to a intuition to to consider this plausible fact, that a plausible conjecture that this leakage, these paths, this will have more leakage because there is a shorter lower permeability path. Here the low permeability paths are going to be much longer. Okay. So, you will probably require much more current to create leakage fluxes here than here. Okay. So, what we can expect intuitively is that the transformer which is short or fat has got in fact more leakage flux than the transformer which is tall. Okay. So, otherwise of course, the transformers are identical, they have the same number of turns on the primary and secondary, and the dimensions are the same, except that this is wound on the longer limb, whereas here the windings are wound on a shorter limb. Okay. So, these are kind of thick, this is a thick bunch of coils, the same coils are spread over this. Okay. So, if you look at this actually we of course, these arguments which I gave you were more intuitive, I did not actually work out the fluxes, but my student in fact tried to obtain the flux pattern using a computational package which uses these Maxwell's equations to actually in a magnetostatic situation, because we are considering constant currents, and he has assumed that the currents flow in coils in the small rectangle which is shown here, and if you have got current flow in these coils, how will the flux lines look like? Okay. So, the magnetic flux density lines are shown here. Most of the flux of course flows in the ferromagnetic core. What is shown here in blue is the flux which is flowing through the air path, and you see the flux density, which is kind of indicated by the number of lines, the density of the lines here. You will find that there is much more flux going in the air path in between these two limbs. Okay. For the taller transformer, you see that the amount of flux density which is leaking out and not flowing into this limb is in fact much lower, and so you will in fact have lesser leakage flux. This appears black not because it is made black, but in fact because of the fact that the flux density lines inside the core are much more dense. So, that is why it appears black. So, what it really shows is most of the flux flows along the ferromagnetic path, but what you are seeing is here is what flows outside. Okay. What flows outside is much higher in the short transformer compared to the tall transformer. Yeah, but the transformer otherwise is both the transformers in all other aspects are identical. Yeah. So, what we do is a simple test which can be done is to try to compute this leakage flux. The fact that this in fact has more leakage flux than the other is actually try to experiment by actually constructing these two transformers. So, we have got a tall transformer and a fat transformer, and we apply a voltage, the same voltage to both the transformers, and we need to actually construct an experiment or conceive an experiment which will actually tell us which of the transformers have high leakage. Both the transformer windings have the same resistance because they use the same conductors, and the number of turns also are the same. So, the resistances are equal, but if in case one transformer has more leakage, it will in fact manifest in some performance measure. Now, actually how do we represent leakage in a transformer? Remember that the leakage flux is the flux which does not link both coils. Okay. So, transformer action in fact does not take place for the flux which does not link both coils. Okay. So, some of the flux which does not link both coils is exclusively associated with the current in that particular winding. So, it is like a small self inductance of these windings which does not take part in the transformer action, and a representation of that is shown by a series inductances on both sides of a transformer. So, before I tell you what actually happens, what kind of experiment I am going to have, remember that the leakage effects can be represented by these series inductances which do not take part in transformer action. So, they are just some fluxes of course linked with the first coil, but does not link with the second coil. You can represent it as a leakage inductance. Okay. So, this is called a leakage inductance. If your current does not flow in the secondary, there will be no leakage flux which is associated with the currents of the secondary. Okay. So, there will be no voltage drop here. So, in fact, because there is a flux which does not link both windings, your V1 by V2 is not equal to N1 by N2, and this in fact series inductance will have a voltage drops which prevents V1 by V2 being equal to N1 by N2. So, this is still our ideal transformer. This represents eddy current effects and hysteresis effects. This is the fact that the self inductance of the winding is not infinitely large. There is some open circuit current, even if I keep the secondary open, some current will flow through this. Okay. This leakage represents the fact that there is some flux which flows, which is linked to the first winding, which does not link with the second winding. So, this ideal transformer has to kind of take out these effects and represent them as inductances which are connected in series. These two inductances are not linked. Okay. There is no mutual inductance between them. So, what you have essentially is, so if I want to actually show that the leakage fluxes are more for a a certain transformer, I can carry out a simple test. The simple test is like this, it is called a short circuit test. So, if you actually compute the short circuit test, what you are going to do is take a transformer, apply a sinusoidal voltage, this is your transformer model, this is an ideal transformer which satisfies the N1 by N2 relationship. So, I have abstracted out all these non-idealities, this is leakage, this is the fact that open circuit current is not 0, this is the eddy, this is called a magnetizing current, this is a resistance which represents eddy current effects. This is an ideal transformer which in sinusoidal steady state V1 by V2 is equal to N1 by N2 and I1 by I2 is equal to minus N2 by N1 if I2 is flowing into the dots. Okay. So, this is V1, this is V2, this is ideal transformer, okay, and all the non-idealities are abstracted out. So, this is called leakage. So, if I want to get an idea about whether if your leakage is increased, what I can do is actually short this secondary, apply a very low voltage. If a very low voltage is applied and this current is negligible, then what you have is simply an ideal transformer and this is the leakage, this is leakage, you have shorted this. So, if you look at it from the primary, this is an analysis we have done before, you have got L1 and L2 into N2 by N1 by N2 whole square. Okay. So, this is something we have done for the resistive load if you recall. Okay. So, if in case the leakage is more, what we will find is that the current flow is going to be less. So, if leakage is more, current is going to be less in case you carry out this short circuit test. So, the short circuit test is in fact carried out and for both the transformers they are identical transformers. The only difference between the two transformers is in fact one has got more leakage and the other one has less leakage. The taller one has less leakage, the shorter one has more leakage, and we will test this conjecture by actually doing this experiment. Okay. So, what I have got is I have short circuited the secondary and I am measuring the current. The LV side in fact is short circuited as I have shown and I am measuring the LV side current. Remember that the currents on the primary and secondary are approximately related by N2 by N1, the turns ratio, assuming of course that the magnetizing current is low, which is in fact true in this case. So, what you find is that if I do this experiment, you find that in case you take the tall transformer, the leakage, the impedance which is seen, the short circuit current is 1.5 amperes, whereas for the short transformer it is 0.94. So, leakage is more here compared to this. Remember that the resistance of both windings is the same, they are identical in all other aspects. Okay. So, only one of them is the windings are wound on the taller limb and one they are wound on the shorter limb. So, it is a very interesting experiment which shows that the leakage in one of the transformers is going to be higher than the other, although they are similar in all other aspects. Okay. So, with this this really we show this represent these leakages as I said some time back using inductance which there is no mutual coupling. So, this is the ideal transformer and we have abstracted out all the non-idealities. Okay. In fact, one more non-ideality which I have already mentioned, but I did not explicitly represent it, is the resistance of the windings here. Okay. So, resistance also plays a role. In fact, if you do a short circuit test, you are actually measuring not only the sum of the impedance caused that is j omega L1 plus j omega L2L referred to the primary, but you are also having R1 plus R2 into N1 by N2 square. Okay. So, in fact, the short circuit current which we in fact includes the effect of the resistance, but the resistances are equal. So, the fact that the currents turn out to be different implies that this and this are in fact different. Okay. So, this is an interesting current which you could consider this is an interesting experiment which you could consider trying to do. You will have to actually construct these transformers and make them, of course, which we have done. The rest of the aspects of transformers, which include 3-phase transformers and in fact inversion magnetizing current effects, is something we will consider in the next lecture.